So this lesson is all about the pH of salt solutions. What we're going to see is that you don't necessarily have to have something that you would categorize as an acid or a base in solution to get a pH that is not neutral. And we're going to explain how that arises. So the first thing we want to do is we want to review the concept of a salt. What is a salt? Well, another name for it is just an ionic compound. We use the term salt because that's the ionic compound that's created when an acid and a base react with each other. So an ionic compound or a salt is composed of ions. You have the positive ions and the negative ions. Those ions can be monatomic like chloride or fluoride, but they can also be polyatomic like ammonium and phosphate, right? So these are just some examples of various salts, also known as ionic compounds: sodium chloride, calcium fluoride, ammonium phosphate. So to understand this lesson, you do need to remember the polyatomic ions that you learned in Chem 1. So if you're not confident that you can recognize the formula of a polyatomic ion and remember its charge, then it may be good to pause the video and go back and review that from Chem 1 a little bit. So I said earlier that the reason why we call them a salt is because that's the term that's used as to indicate one of the products of an acid-base reaction. So anytime you have an acid and a base reacting with each other, you produce two things. You produce water and you produce a salt, which is essentially the ions that are left over from the formation of water. So for example, let's say that I have this acid, hydrochloric acid, reacting with this base, sodium hydroxide. Well, the hydrogen from the acid and the hydroxide from the base combine to form the water, and then the ions that are left over form the salt. So in this case, we've got the chloride left over here and the sodium ion left over here, and they come together to form sodium chloride, the salt. So here's the deal. Some of the ions that are part of the salt might go on to react with water. Why would they do that? Well, if those ions are related to a weak acid or a weak base, more specifically, if they are the conjugate base of a weak acid or the conjugate acid of a weak base, then they'll go on to react with the water molecules, and that will lead to a non-neutral solution. Okay, so for example, let's say that we have a fluoride ion as one of the ions in our salt. Well, fluoride is the conjugate base of a weak acid, hydrofluoric acid. I know a lot of times the students get confused about that and they think that HF is a strong acid. It's not. So once again, you need to have that list of strong acids memorized so that you can compare any other acid against that list and know that, therefore, that it's a weak acid. Okay, and hydrofluoric acid is not on your list of strong acids, so it's a weak acid, and so therefore fluoride is the conjugate base of a weak acid. Now, because of that, it will behave as a base in water, and that's what we see here in this reaction. So the fluoride, we said it was the conjugate base of a weak acid, so it's going to behave as a base. Well, what do bases do? They accept H+. So this fluoride is going to take on an H+ from a water molecule, making HF, hydrofluoric acid, but more importantly, what's left over from the water molecule is the hydroxide ion, OH-. And so that's why we say that a solution that has fluoride ions in it will be basic. It will have a pH greater than 7 because of the hydroxide ions that are produced when the fluoride ions react with the water. And again, the reason why they react with the water is because this ion is the conjugate base of a weak acid. So it's related to something that is weak, a weak acid, or if an ion was related to a weak base, you would have also a different reaction with water. Okay, so the best way I think to learn this information is just to do lots of examples. And so that's what we're going to launch into next. Okay, but if you prefer, there is this table right here, which kind of condenses it all. And feel free to memorize these three columns anyway, if you want, that if your salt has the anion of a strong acid and the cation of a strong base, you get a neutral solution. If it has the anion of a strong acid, but the cation of a weak base, you get an acidic solution. If it has the anion of a weak acid and the cation of a strong base, you get a basic solution. And if you have the anion from a weak acid and the anion and the cation of a weak base, then it could be any of the three. But what you do is you compare the Kas of the acids and bases involved, and that will give you the determination. Okay, so if you want to take that route and just kind of memorize the contents of this table, you can. but I think it's best if you just kind of reason through, look at the formulas and reason through it and get to the same answer. So here's what we're going to do with the as some examples. So this is the question: will these salts, will potassium bromide, ammonium chloride, sodium cyanide, and ammonium nitrite, will solutions of those salts be acidic, neutral, or basic? Okay, so the first skill you need to have is you have to know what the compound is going to break apart into when you put it in water. So for example, KBr, if I put it in water, if I dissolve this KBr in water, what do I get? I get potassium ions and I get bromide ions, okay? So then the next thing you need to do is you need to analyze each of these ions and determine if they come from a strong base and strong acid, a weak base and a weak acid, or some combination. And so let me kind of illustrate how you do that. So the idea here is you need to imagine if each thing came from a base, what base would it be? And if something came from an acid, what acid would it be? So for example, let's take this potassium ion. So the cations, they're going to come from a base. So if it did come from a base, which base would it have come from? Well, the best way to answer that question is just to slap a hydroxide onto the formula. So it would be KOH. Okay, so potassium hydroxide. And then you just categorize this base. Is this a strong base or is this a weak base? Well, potassium hydroxide is a strong base, and we know that because remember, potassium is in group 1 of the periodic table, and all group 1 and group 2 hydroxide compounds are strong bases. So all hydroxides where the metal ion or the cation is from group 1 or group 2 will be a strong base. So this is a strong base, okay? And so the conclusion then is that NR means no reaction. So this ion is not going to go on to react with water because it comes from a strong base. So let's do something similar with the Br minus. So what I need to figure out is, well, if this did come from an acid, let's imagine that it came from an acid. Which acid did it come from? Well, it came from HBr, hydrogen bromide. And so then I just compare that against my memorized list of strong acids, and I remember that hydrobromic acid, HBr, is a strong acid. And so once again, this ion will not go on to react with water either. Okay, so if that's the situation, then what you have is you're going to have a solution that is neutral. Okay, because neither one of these ions react with water. So it leads to a neutral solution. Okay, so we analyze this and we figured out the potassium comes from KOH, which is a strong base. We analyze the bromide, we slap a hydrogen onto it, and it comes from that acid, so hydrobromic acid, which is a strong acid. And so because of that, neither of those ions, neither the potassium nor the bromide will react with water. And so we end up with a neutral pH or a neutral solution. All right. What about the ammonium chloride? What happens to it when I put it in water? Well, it breaks apart. It dissolves in the water and breaks apart into ammonium ions and chloride ions. So now let's analyze each ion. So this ammonium ion, we're going to imagine that it came from a base. So if it did come from a base, which base did it come from? Well, it would have come from ammonia, NH3. What do bases do? Remember that the definition of a base is it accepts H+. So if ammonia, NH3, takes on an H+, it becomes NH4. So if this ammonium ion came from a base, the base that it came from is NH3, ammonia. Well, I remember that that is a weak base, okay? And so the consequence of that is that this ion will go on to react with water, and it will react with water, okay? So it reacts with water, and it does so in this way. We've got the ammonium ion, so NH4+, and it's going to react with a water molecule in a reversible way. So this is the conjugate acid of a weak base. So what do acids do? They donate H+. So this conjugate acid, this ammonium ion, is going to donate an H+ to the water molecule to give me a hydronium ion, H3O+, and then the other product would be ammonia, NH3 aqueous, okay? All right, so the key here, though, is that I produce these hydronium ions. So this means that the solution is going to be acidic, all right? Now, to just, fully prove that, I also want to think about my chloride ion and what happens there. So with the chloride ion, if it did come from an acid, remember we just slap a H onto the formula, so that would be HCl. Well, I memorized that that's a strong acid. And so therefore, the chloride ion is not going to react with water. Okay, so the ammonium ion does react with water and gives me some hydronium ions as a result of that reaction, which means that the solution is going to be acidic. So ammonia would give us ammonium ion. Ammonium ion, if it were to come from a base, comes from ammonia, which is a weak base. And then the chloride ion comes, if it were to come from an acid, comes from HCl, hydrochloric acid, which is a strong acid. Okay, well, that means that they're not going to get any reaction from the chloride, but we will get a reaction with water from the ammonium ion. So the ammonium ion will react with water, and it does so by this reaction. The ammonium ion finds a water molecule, reacts with it in a reversible way to give us the hydronium ion and an NH3, and that's the key thing is the hydronium ion. So that will lead to an acidic solution. Okay, what about this one, sodium cyanide? So once again, if it were dissolved in water, it would give us sodium ions and cyanide ions. We analyze the sodium ion. If it were to come from a base, which base would it come from? We just slap a hydroxide onto the formula, so NaOH, and I memorize that that is a strong base. Sodium hydroxide is a strong base, so we're not going to get any reaction with water from the sodium ion. Now we do something similar with the cyanide. So if it were to come from an acid, I just slap a hydrogen onto the formula, so it would be HCN, hydrocyanic acid. So that is not on my memorized list of strong acids. So that means that it is a weak acid. And so the thing about that is this will go on to react with water. Okay, and the reaction will look like this. So that Cn minus is going to react with water. So it finds a water molecule and reacts with it in a reversible way. So since this is my weak acid, the Cn minus is the conjugate base of a weak acid. So it's going to behave like a base. It's going to do what bases do. Bases accept an H plus, so it becomes HCN, and then what's left over on the water molecule, because one hydrogen was stripped away, what I'm left with is a hydroxide ion. Okay, and that's the key, because if you have an excess of hydroxide ions, that means you end up with a basic solution. Not an acidic solution, not a neutral solution, a basic solution. Okay, so once again, the sodium ion, if it did come from a base, comes from sodium hydroxide, which is a strong base, so it's not going to react with the water. Cyanide, if it did come from an acid, it came from hydrocyanic acid, or HCN, which is a weak acid. So that means that the cyanide ion, the Cn minus, will go on to react with water. And this is the way that it does that. It is a conjugate base. So it reacts with water in a reversible way to give me HCN, but more importantly, it gives me the hydroxide ion. Okay, so that means that the solution is going to be a basic solution. It's going to have a basic pH. Okay, so finally, let's look at the situation where we have two ions produced that both react with water. And how do you deal with that? So this is a compound known as ammonium nitrite. And so hopefully you can realize and see that when ammonium nitrate is dissolved, you get two ions. You get ammonium ions and you get the nitrite ions. And so once again, we just analyze these ions to think about the base and the acid that they would have come from. So for the ammonium ion, we've already kind of done this. So if it did come from a base, it would have come from ammonia, NH3, which we know is a weak base, okay? So it will go on to react with water, okay? And so the way in which it's going to react with water is like this. So the ammonium ion reacts with a water molecule in a reversible way. It's a conjugate acid of a weak base, so it donates H plus to the water molecule to give me H3O plus hydronium ion, and then the other product is ammonia, NH3. So the key is you get those hydronium ions from that. Well, what about the nitrite? If it were to come from an acid, you just slap a hydrogen on the formula, which is HNO2, okay? And that is nitrous acid, which is a weak acid, okay? It's similar to the HNO3, which is nitric acid, which is a strong acid, but make the distinction. This is HNO2. So it's nitrous acid, which is a weak acid. So that means that it is also going to go on to react with water. And it is the conjugate base of a weak acid. So the reaction for the nitrite will be the reaction of a base. So the nitrite finds a water molecule, reacts with it in a reversible way as a base would do. Bases accept H+. So it grabs an H+ and becomes HNO2. But then what's left over from the water molecule is the hydroxide ion, OH-. Okay? So here's the dilemma that we have. We have one ion producing hydronium ions, and we have the other ion producing hydroxide ions. So the question is, well, which one is going to dominate? So is the solution going to be acidic or is it going to be basic? Well, what you need to do at this point is you compare the equilibrium constant. So you compare the Ka of the reaction that generates the hydronium with the Kb of the reaction that generates the hydroxide. And whichever one is bigger is the dominant reaction, and therefore will determine if the pH is acidic or basic. Okay, so once again, the ammonium ion, if it were to come from a base, comes from ammonia, which is a weak base. The nitrite ion, if it were to come from an acid, comes from HNO2, which is nitrous acid, which is a weak acid. So each of those ions will go on to react with water. Okay, so ammonium ions and nitrite ions will react with water. And so, as I said, what you need to do at this point, I didn't write the reactions here in PowerPoint, but you got them with the handwriting. You compare the Ka of the ammonium ion, because that's the ion that generates the hydronium, the H3O plus, right? So compare that Ka of 5.6 times 10 to the minus 10 with the Kb for the nitrite, because that's the ion that generates the hydroxides, right? It's the nitrite reacting with water that gives you hydroxides. So it has a value of 2.2 times 10 to the minus 11. Okay, so the Ka is bigger, right? 10 to the minus 10th is a bigger number than 10 to the minus 11th. So what that tells us is that the acid reaction is going to be dominant, and so it leads to an acidic solution. So since the Ka is larger than the Kb, that tells you you're going to have an acidic solution. Okay, so now we need to utilize this information to do calculations about pH. So these are ions that behave as weak acids or weak bases. And so we know that in order to do calculations, we're going to need to set up a rice table. Okay, so what I know is going to happen is that this potassium fluoride is going to dissolve in water, and 100% of it will transform into potassium ions and fluoride ions. Okay, so if I have 0.15 molar potassium fluoride, then that means that I have 0.15 molar potassium ion and 0.15 molar fluoride ion. And that's the most important one, because we're going to use that number in our rice table, because this is the ion that I know is going to go on to react with the water. This, is the ion that reacts with water. Okay, and this is the reaction that occurs. I have the fluoride ion reacting with a water molecule in a reversible way to give me HF, and more importantly, the hydroxide ion. Okay, so this is the reaction at the heading of my table. So I go ahead and finish out my rows and my columns for my table. I ignore the column for the water because it's a pure liquid. And as I said, the concentration of fluoride ion is 0.15 molar, and none of that. And in the same pattern here, it's going to shift to the right because I don't have any of these products. So I'm going to lose X amount of the fluoride ion, gain X amount of these two products. So I bring my columns down, 0.15 minus X, X, and X. And so then I know that the expression for this reaction is a Kb, right? Because this is a reaction of a base, generates hydroxide. So it's going to be concentration of HF times concentration of hydroxide over the concentration of fluoride. And I substitute in the terms for my E row. So that becomes X squared over 0.15 minus X. Okay. And in the next, I'm going to let PowerPoint kind of take over from here. But what we can say here is that this Kb, two things. It might be given, or if I need to calculate it, if I'm given the Ka, remember the relationship here is that the Kw equals Ka times Kb. And so even if, for example, I'm given the Ka of hydrofluoric acid, I can calculate what the Kb of the conjugate base, which is fluoride, by using this relationship here. And you'll see that in the PowerPoint solution that I present here in just a second. And so I'm going to let PowerPoint take over from here. Okay, so again, the potassium fluoride, when it dissolves, breaks apart into potassium ions and the fluoride ion. I recognize that the fluoride ion is a conjugate base of a weak acid, so it will behave like a weak base when it's dissolved in water, and therefore I need a reaction that's going to produce some hydroxide ion. So there's the reaction. The fluoride ion acts as a base. When it finds water molecules, it rips off H plus becomes HF, and then also as a byproduct gives me hydroxide ion. So that is also the reaction that I work with in my table. And because of the molarity relationship here, if I have 0.15 molar of potassium fluoride, I have 0.15 molar of the fluoride. So that's where I get that number there, 0 and 0, minus x plus x plus x. Bring the columns down, substitute that into my expression for the Kb. Okay, now as I said before, this comes from the fact that the Kb times Ka equals Kw. So this number right here, the 1 times 10 to the minus 14, remember that that is, this is Kw, right? And this is on your equation sheet. You don't need to memorize that, okay? But just to know where we got to this point, Kw equals Ka times Kb. And even though it's not real clear, you know, I should have put it in the problem statement. It's like this was given. This is the Ka, okay? And I'm going to assume that this was given, or I got it from a table or something like that, and then I use it to calculate the Kb. Okay, so this is the number that I'm going to use to do the actual calculation. Okay, so I substitute in my terms from my table to get the x squared over 0.15 minus x equals this Kb that I just calculated. Okay, and so now I recognize that I can use the approximation method, because if I multiply this Kb times 100, it's still smaller than this 0.15. So I can just ignore this minus x. And that makes the math a little simpler. So I just end up multiplying both sides by 0.15, cancels over here, changes that number. Then I just take the square root of both sides, and that makes this x, and then it's the square root of that product over there. And so if you solve for x, you get a value of 1.47 times 10 to the minus 6, which if you look at your table, that value of x is the equilibrium hydroxide ion concentration. So I can't go directly to a pH. Remember, the question is asking for the pH. But I can go directly to a pOH, which I can then subtract from 14 to answer the question and get the pH. Okay, so the pOH is just the negative log of that number, which is 5.83. So then I just subtract that from 14, and you get a pH of 8.17. And again, you can always reality check that answer, because I suspected that this was going to be a basic solution. It would have a pH higher than 7, because this fluoride ion is going to behave as a weak base. It is the conjugate base of a weak acid, so in solution it behaves as a weak base, which that should lead to a solution with a pH greater than 7, and yes, my calculation confirms that. Okay, so the problem that I gave you to do at the end of class is this one. So what is the pH of a 0.0697 molar solution of NaOCl, which is sodium hypochlorite, which is the active ingredient in bleach? And I tell you to use your Ka/Kb table to come up with a constant that you need. But the first thing to recognize is, which of these ions is going to affect the pH. Okay, so we start there. So the sodium hypochlorite, NaOCl, if I put it in water, it gives us a sodium ion and a hypochlorite ion, OCl minus. Okay, well, the sodium ion, if it comes from a base, it comes from sodium hydroxide, which is a strong base, so the sodium ion is not going to react with the water. The hypochlorite ion, if it comes from an acid, comes from HOCl, which is hypochlorous acid, which is a weak acid, so this ion, the OCl minus, is the one that's going to go on to react with water. Okay? It is the conjugate base of a weak acid, HOCl, hypochlorous acid. So just like fluoride, it will behave like a weak base in water, producing some hydroxide ion. Okay, so this is the reaction that occurs. So that hypochlorite ion, the OCl minus, behaves as the conjugate, or behaves as a base, because it is the conjugate base of a weak acid. So it finds a water molecule, reacts with it in a reversible way to give us the hypochlorous acid, but more importantly, it gives us the hydroxide ion, leading to a basic solution. So that becomes the reaction at the heading of my rice table. So then I plug in all my numbers. I've got the molarity value. I put that there, X that out, 0, 0. And then as before, it's going to shift to the right. So minus X plus X plus X. And I just bring the columns down. Now I'm going to take these terms in my E row, and I'm going to substitute them into the expression for the Kb. So you get this. Okay, so then I look up in a table, the Kb, there's two ways you could do this. You could look up the Kb of the OCl minus in a table, or if you look up the Ka of hypochlorous acid and then solve for Kb, with the equation like we used in the previous example, you could do it that way, but it's much easier if you just use your table to look up the Kb of this hypochlorite ion. So if you do that, you find that it's equal to 2.9 times 10 to the minus 7. So once again, if I multiply that times 100, it's much smaller than this number that I'm subtracting from, so I can approximate. And so then I just multiply both sides by 0.0697, and I take the square root of both sides to solve for x. And if you do that, you get 1.42 times 10 to the minus 4, which once again, if you look at your table, is a hydroxide ion concentration. So I can change that to a POH, take the negative log of that number, and it gets me the POH. And I subtract that from 14, and I get the pH. So the pH is 10.15.